Welcome to AI Paper Podcasts, where we break down the latest research so you can stay ahead. Today, we're tackling a really common headache in AI deployment: large language models.
Yeah, they're amazing tools, no doubt.
Absolutely. Incredibly powerful. But they also come in all shapes and sizes, right? Different skills and, crucially, very different price tags.
That's the kicker, the cost.
Exactly. It's definitely not a one-size-fits-all situation.
Yeah.
So the big question is, how do you make sure you're using the right LLM for the right job without, completely blowing your budget?
It's a huge challenge, and that's precisely what today's paper dives into. We're looking at adaptive LLM routing under budget constraints by Pranoy Panda, Raghav Magazine, and their colleagues from Fujitsu Research and Microsoft Research.
Sounds fascinating. They're tackling that exact dilemma, the performance versus cost balancing act.
They really are. And they've come up with some pretty clever ideas.
Okay, so before we dive deep, let's do the quick summary, the kind you might use for a short clip. The core issue here is that traditional LLM routing, well, it's often treated as a supervised learning problem.
Right, which means you need tons of labeled data, which is expensive to create, and these systems aren't great at adapting when users start asking new types of questions.
And this paper?
They flip the script. They reframe LLM routing as a contextual bandit problem. Think about like a news recommendation system that learns what you like just from you clicking on an article.
Okay.
Here, the system learns from really simple feedback, like a thumbs up or thumbs down on the LLM's answer. It makes it super adaptive and, importantly, much cheaper to train and run.
And they've got an algorithm for this.
Yep, it's called PILOT. That stands for Preference Prior Informed LinUCB for Adaptive Routing. It's smart because it combines some initial knowledge gleaned from human preference data with continuous learning on the fly.
So it gets a head start, but keeps improving.
Exactly. And crucially, PILOT also includes this novel online cost policy. Think of it like a budget manager that learns. It uses something called a multi-choice knapsack formulation to dynamically manage the budget you set.
The knapsack problem. Okay, keeping costs in check. So what's the payoff?
The results are pretty impressive. On benchmarks like RouterBench, which has lots of different tasks, PILOT got about 93% of GPT-4's performance.
Wow, 93%.
And this is the big part, and only 25% of the cost of running GPT-4 for everything. It performs better and makes fewer bad choices, less regret, compared to other methods. It really feels like a step forward for actually using these models efficiently.
Okay, 93% performance at a quarter the cost.
Sure.
That's definitely a game changer. Let's unpack that real-world problem a bit more, this LLM balancing act. The potential of LLMs is just massive. We all see that. But anyone who's tried to put them into a real product hits this wall pretty quickly. Performance versus cost. You've got the big models, like GPT-4, often give you better answers, especially for complex stuff. But wow, they are expensive to run.
The inference costs add up fast.
They really do. And then you have smaller, cheaper models, much easier on the wallet, but they might just not be good enough for the tricky questions. They might fail completely.
Yeah, they might not cut it.
So think about a customer service chatbot, maybe one you're building. Someone asks, what are your opening hours? A small, cheap model. Perfect. Does the job, saves you money.
Simple query, simple model, makes sense.
But then the next query comes in. Okay, I need a really detailed comparison between your X200 and Z300 phones.
Yeah.
Focus on battery, camera, multitasking, and tell me the downsides of each.
Whoa, okay, that's much more involved.
Exactly. For that, you really want the power of something like GPT-4 to give a good, nuanced answer. But if you use GPT-4 for the opening hours question too, you'd be burning cash unnecessarily.
You'd go broke pretty quick running GPT-4 for every single interaction.
Right. You need that dynamic routing. You need something smart deciding which model gets which query.
And that's where older approaches fall short. Modeling it as a standard supervised learning problem just creates headaches.
How so?
Well, first, you need those huge, expensive labeled data sets. You have to figure out, for thousands or millions of example queries, which LLM is actually the best. That often means running all your models on every query during data collection just to find the winner.
Oof, that sounds incredibly inefficient.
It is. It's a massive bottleneck. And second, these supervised systems, they're static. They learn based on the data you gave them. When the kinds of questions your users ask start to change, and they always do, the system doesn't adapt well. Its routing choices become suboptimal.
Okay, so that lack of adaptability is a killer in a field moving as fast as LLMs.
Precisely. Which brings us to the really interesting part of this paper. They looked at this problem and thought, well, what about news recommendation?
News recommendation, how does that connect?
Think about it. A news site doesn't show you every single article it has and ask you to rate them all. That'd be overwhelming.
Right. It just shows you one or a few.
Exactly. It shows you one, sees if you click, maybe how long you read it. That's the feedback. And it learns from that single interaction. Very efficient.
Ah, I see where you're going. Limited feedback, but you still learn.
Yes. They apply that insight. They reformulate LLM routing as a contextual bandit learning problem. Instead of needing outputs from all your LLMs, the system just needs simple binary feedback on the one LLM it chose.
Like the thumbs up down you mentioned.
Exactly like that, which is super practical, right?
Yeah.
Lots of chat interfaces already have those feedback buttons.
Yeah, that's true. Much easier to get than asking someone to compare 5 different outputs.
Way easier. So formally, the setup is you have K LLMs, a query QT comes in, represented as an embedding, like a vector X. There's some way to score the quality of the response, let's call it S. The router, M, picks an LLM, LL. It gets a reward based on the quality score, and it also knows the cost clit for using that LLM.
Okay, makes sense. Reward and cost.
And the goal, maximize the total reward, the sum of all or over a whole bunch of queries, say Q queries, but crucially, without spending more than your total budget be.
Maximize quality, stay within budget, the core dilemma. So how does Pilot actually figure out which LLM is a good match for a query, especially if it's learning from just that simple feedback? Right. Does it start like totally naive?
That's a great question. It doesn't start completely blind, and that's key to Pilot's success. The core idea is creating this evolving shared embedding space.
An embedding space.
Yeah, think of it as a map. They map both the queries and the LLMs onto this map. Queries that are similar in meaning end up close together. And LLMs that are good at similar types of queries also end up close together.
Okay.
And crucially, an LLM's point on the map should be close to the points of the queries it's good at answering. The closer a query's point is to an LLM's point measured by cosine distance, usually the better the match, the higher the affinity.
And this space evolves, it changes.
That's right. It's not fixed. It refines itself as the system gets more feedback, learning better representations over time.
Clever. How do they build this initial map, though?
They use a really smart two-phase pre-training process. It gives Pilot that head start we talked about. Phase 1 is about learning query projections.
Projecting the queries onto the map.
Exactly. They take a standard query embedding, maybe from something like OpenAI's text embedding 3 small, or Instructor XL, a good general purpose embedding, and they learn how to transform it, project it into their special shared space.
How do they learn that transformation?
Using Triplet Loss. This is pretty neat. They use existing human preference data, like from datasets like Chatterina, where people have compared LLM outputs. For a given query, they find an LLM that a human preferred. That's the anchor and positive.
Okay.
Then they find a hard negative. This could be another LLM that was not preferred. But they also specifically look for cases where a smaller, cheaper LLM was preferred over the current winning LLM. This helps teach the projection not just about quality, but also about cost efficiency from the get-go.
Building in the cost aspect early.
Yeah.
Smart. What's phase 2?
Phase 2 is learning the LLM embeddings. Now that they know how to project queries onto the map, that projection part's frozen, they learn the specific location, the embedding fee, for each LLM lie on that map.
So placing the LLMs on the map near the queries they're good for.
Precisely. The goal is to make the preferred LLM's embedding end up close to the query's projection. They treat this like a binary classification task using binary cross-entropy loss. This results in an initial preference embedding for each LLM, sort of its starting position reflecting its known strengths and weaknesses based on human judgments.
Okay, that pre-training sounds incredibly powerful. It gives Pilot a really informed starting point instead of just random guessing. But then, how does it keep learning once it's live, getting that thumbs up, down feedback?
Right, the pre-training is the foundation, then comes the online learning. This is where the contextual multi-armed Bandit CMAB framework really comes into play.
The Bandit problem again.
Yep. The projected query embeddings, those points on the map we just talked about, they serve as the context for each decision. They tell the system about the specific nature of the query.
Okay, context is the query type.
And the available LLMs are the arms of the Bandit, the choices the system can make. Pulling an arm means selecting an LLM.
And the reward.
The reward is based on that simple feedback, the quality score derived from the thumbs up down, usually scaled between 0 and 1.
Got it.
Now, because the expected reward is modeled as that cosine distance, how close the query and LLM are on the map, it fits nicely into a linear reward model. This allows them to use an algorithm based on LinUCB, which is a standard and effective Bandit algorithm.
LinUCB. I've heard of that. It balances trying new things and sticking with what works, right? Exploration and exploitation.
Exactly. But Pilot is a novel extension of LinUCB. The key difference is the preference prior informed initialization.
Using the results for the pre-training.
Precisely. Instead of starting LinUCB with zero knowledge about the arms, the LLMs, Pilot initializes the parameters for each arm using those pref embeddings learned from the human preference data in phase 2.
So it starts with a strong hypothesis about which LLMs are good for what.
Yes, it acts like a Bayesian prior. It's an informed starting estimate. It doesn't have to explore randomly for ages. It already has a good idea based on data where to start. They even cleverly adjust how much they trust this prior based on how well the LLM performed during pre-training using a regularization parameter RIA.
That sounds much more efficient.
It is. The algorithm then does the standard UCB thing, upper confidence bound, selecting the arm, LLM, that maximizes a combination of its estimated reward and an uncertainty bonus, encouraging exploration of less certain but potentially good options.
And does this prior actually help in theory?
They show theoretically that yes, this preference prior informed approach can achieve a smaller regret bound. That means over time, it's guaranteed to make fewer suboptimal choices compared to a standard LinUCB starting from scratch, provided that initial prior knowledge is reasonably good.
Fewer mistakes, better overall performance.
Yeah, exactly.
Okay, so it learns smartly, it starts smartly, but we keep coming back to the budget. How does that fit in with the Bandit decisions?
Right, you can't ignore the budget. A super smart router that bankrupts you is useless. Pilot integrates a dedicated online cost policy to handle this explicitly. You tell it your total budget B over Q queries.
And it manages it on the fly.
Yes. They frame this part as an online multi-choice knapsack problem.
There's knapsack again.
Yeah, it's a great analogy. Your total budget B is the knapsack's capacity. Each time a query comes in, you have a choice of items to put in the knapsack, the different LLMs. Each LLM has a value, its estimated reward, and a weight, its estimated token cost. You want to pick the LLM that gives you the best value without exceeding your budget capacity over time.
But queries keep arriving, so you can't plan it all out perfectly at the start.
Exactly, it's online. So they use a binning strategy. They divide the total number of queries Q into n smaller bins or batches. Each bin gets a proportional slice of the total budget, Bn.
Okay, breaking it down.
And smartly, if you don't use all the budget in one bin, maybe you got easy, cheap queries, the leftover budget can spill over to the next bin. It adds flexibility.
Nice. So for a specific query, how does it decide which LLMs are even allowed, cost-wise?
For each incoming query, the policy looks at the available LLMs. It calculates a dynamic cost threshold. This threshold isn't fixed. It depends on the LLM itself, its current estimated reward from the Bandit part, and importantly, how much budget is left in the current bin and overall.
So it gets stricter if the budget is tight.
Potentially, yes. It identifies the eligible LLMs, those whose estimated cost is below this dynamic threshold. Then, from that subset of affordable LLMs, the main pilot algorithm, the LinUCB part, picks the one with the highest UCB score, the best expected performance among the affordable options.
Ah, okay. So it's a two-step filter. First budget eligibility, then best performance among those eligible.
You got it. It ensures resources are allocated dynamically to maximize reward while respecting the budget constraints. It's constantly juggling cost and quality based on the current situation.
That sounds incredibly practical for real-world deployment. So the million-dollar question, or maybe the $250,000 question, given the cost savings, how did it actually perform in tests?
Right, the proof is in the pudding. They tested Pilot using the Router bench dataset. It's a pretty challenging benchmark, covers lots of ground, common sense reasoning, coding, math, multi-turn chat.
Diverse tasks.
Very diverse. And it uses responses from 11 different LLMs, a real mix, including GPT-4, Mixtral, Claude models, LlamaSunDB, a good representation of what's out there.
Okay, so what did they find?
The results were really strong, backing up the claims. Let's break it down. Performance versus cost. This is the headline. On the multitasked Router bench, Pilot got that 93% of GPT-4's performance at only 25% of the cost. On MMLU data alone, it was 86% of GPT-4 performance at 27% cost. That's a massive efficiency gain. Consistently, across different setups, Pilot had the best performance for a given budget and the lowest regret.
That cost saving is just huge.
It really is. And then there's adaptability. They simulated a data shift, switching the task midstream from MMLU, multi-choice questions, to GSM-8K, math word problems.
To see how it handles change.
Exactly. Pilot adapted significantly after the shift. Its performance improved on the new task, while static, supervised methods like hybrid LLM just couldn't keep up. They also saw Pilot's exploration rate spike. During the shift, it realized things had changed and started trying different LLMs more, and then it settled down once it adapted. Clear evidence of effective online learning.
So it's not just cheap and good, it's also resilient. It learns when things change. What about the kinds of decisions it made? Was it actually being smart about routing?
That's what the qualitative analysis looked at. And yeah, it seemed pretty intelligent. For really hard tasks like MMLU or ARC challenge, where you probably do need the best model, Pilot sent about 90% of the queries to GPT-4.
Okay, using the big guns when needed.
Right. But for coding, MBPP, while GPT-4 got used, Claude models handled a good chunk, about 28%. Pilot seemingly learned that Claude is quite strong at coding, offering good value there.
Recognizing specific strengths.
Exactly. And for math, GSM-8K, Claude V1 was the main choice, getting 94% of the queries. Probably because it hits a sweet spot of being good enough for those problems while being cheaper than GPT-4. So it's not just defaulting to the biggest model, it's making nuanced choices based on task and capability.
That really does sound like intelligent routing. What about overhead? Does all this cleverness slow things down?
Good question. Computational efficiency was also impressive. The time taken by Pilot to select the LLM was tiny, negligible really. Depending on the embedding model used for the queries, it was 10 to 38 times faster than the average time it takes GPT-4 just to generate a response.
Wow, so the routing decision itself is super fast. Critical for real-time apps?
Absolutely. Latency matters. They also compared their cost policy to simpler ways of managing budget, like just setting a fixed budget per query, or even comparing it to an offline policy that knew the future perfectly. Their online knapsack approach generally performed better, showing the value of its adaptive nature.
Better than knowing the future. How?
Well, the offline perfect knowledge policy, RFEs, is optimized based on true costs and rewards, but Pilot's policy works with estimated rewards and costs learned online, dynamically adjusting to the budget. In practice, this dynamic adjustment within the bins often led to better overall utilization and reward within the budget compared to a theoretically optimal but potentially rigid offline plan.
Interesting. Any other key findings?
Two more quick ones. They did a query complexity analysis using a metric called evol complexity. They found Pilot routes statistically significantly more complex queries to GPT-4 compared to other standard Bandit algorithms like LinUCB without the prior.
So it's not just routing randomly, it's actively sending the hard stuff to the powerful model.
Seems that way, yes. And finally, embedding model sensitivity. They checked if Pilot's success depended heavily on using OpenAI's embedding model. They swapped it out for Instructor XL, another strong model, and Pilot still outperformed the baseline significantly. It shows robustness.
Okay, that's a comprehensive set of results. It really seems like Pilot delivers. So, stepping back, what's the big takeaway for people listening? Maybe AI researchers, maybe ML engineers, building systems.
I think the big takeaway is that this combination, using prior knowledge from human preferences and then adapting online with efficient Bandit learning while explicitly managing a budget, is a really powerful and practical paradigm.
It makes sophisticated LLM deployment seem much more achievable.
Exactly. Pilot offers this robust, adaptable, and genuinely cost-efficient framework. It moves away from static, expensive supervised routing towards something that learns and personalizes model selection over time. It addresses that core performance cost tension head on.
It really is like having that smart concierge for your LLMs,
All right.
Always picking the right tool, considering your budget, learning your needs. It feels much more managed, strategic.
Well put. And while Pilot is a big step, the authors themselves point towards future work. Things like integrating the budget constraints even more deeply into the Bandit learning itself, not just as a separate policy layer.
Making budget awareness part of the core learning.
Potentially, yeah.
Right.
Or extending it to handle multi-turn conversations more naturally, where the context evolves across several interactions. There's still room to build on this.
Absolutely. You could imagine a future where these systems are even more proactive, maybe even advising you on how to allocate your compute budget based on anticipated query types. It really makes you think, doesn't it?
Yeah.
What other complex optimization problems in AI could benefit from this blend of prior knowledge and adaptive online learning like Bandits?
It's a powerful approach, and it feels like we'll see it applied more and more. Combining the best of offline knowledge with the flexibility of online adaptation seems key.
A fascinating paper and a great discussion. Thanks for breaking down Pilot for us.
My pleasure. It's definitely worth paying attention to.